Hello everybody, welcome. Today we're going to continue with Polygon Triangulation. Last time we gave a general overview of what the ear clipping algorithm could look like, and now we're going to start doing actual implementation, or we're going to start coding this directly. Now I am using C# and Monogame, and I'm also using a library called Flat Engine. You can see the code for that over here. This tutorial is not going to rely on that code. I'm strictly using it for display purposes to get something up on the screen so I can see it. But if you're interested in how this library was created, take a look at my channel and you can see exactly step by step through previous videos how the library was created. Or if you just want the source code, again, we have it here in this Flat Asteroids GitHub repository. There's a folder down here called Flat, and you can click on this and have access to all the source code there, which is freely available for use. And I'll also put a link to it in the description of this video as well. So before we get started actually coding the triangulation function, there's a few helper functions that I'd like to create. The first one I want to create is going to help us get the cross product of two vectors. Everything we're doing is in 2 dimensions, and the cross product isn't technically defined in 2 dimensions. It's a 3-dimensional vector that gives a 3-dimensional vector as a result. And we can bring up what that looks like over here. The cross product is going to be one of those functions that we're going to use over and over and over in lots of different things when we triangulate our polygon. And so it's a very important function for what we do. But in 2 dimensions, it's kind of a pseudo cross product. And you can see here the cross product. In fact, let's bring up this other page here. This is information here about what the cross product is and how to calculate the cross product. And if we scroll down here, you can see how it is actually calculated using vectors. When you calculate the cross product, here's how you get the x, y, and z components. In 2 dimensions, the x and the y are going to go away because our z component is always 0. And so all we're left with is a z component. And we're going to use that z component and basically just return a scalar from our function that'll give us information about how vectors relate to each other. I found this application here that gives a really good visualization of what the cross product looks like. And we're actually doing this, you can see it's a 3-dimensional vector, but it all takes place on a 2-dimensional plane where the z component is always 0 of the 2 vectors. So if you look up here, we have 2 vectors that we're crossing together, and you can see that depending on which way they're facing, we end up with different results here. As the 2 vectors are facing completely opposite directions, I'll go ahead and line them up here so they're facing completely opposite directions. You can see we end up with 0 as our z component. Now the other 2 components are going to be 0 all the time because the z component of their vectors are always 0. So all we're interested in here is this z result. But now as I start to bring this vector and go this direction, you can see I get a positive result. So if we look at the vector pointing from A to C, anytime that the vector pointing from A to B is on the right of that vector, we're going to get a positive result. And then as I go back over here and I start going to the left of that vector, we're going to get a negative result. So as long as I'm on the left of A to C, I'm going to get a negative result. And then the moment I start to go on the moment I'm on the line, I get a 0 result. And then once I'm past the line on the right, anywhere on the right, I'm going to get a positive result. And so the cross product is going to be very important for what we're doing. Let me go here. I'm just going to copy this because this is the only piece we need is just the z component. And it's just going to give us that sign information. You know, what sign do we have when we compare these vectors? And so we're going to provide 2 vectors here. And actually I want to call this B. And here's what we need to return. So this will simply return the A x component times the by component. Then we subtract the ay component times the bx component. So very simple there, but will help us get a lot of information when we're comparing vectors or the edges in our polygon. Okay, and one more function I want to create is going to help us access information inside of our arrays. I want to treat any array that we create. So let's go back here. If this is an array of data, I want to treat this as a circular array. So every time I get past the last item, I want it to loop back to the beginning, or anytime I get less than the first item, I want it to loop back to the end. And let's go back over here. The way that looks is I'm going to create a function, and it's going to just return a generic value, and I'm going to call it get item. for getting an item from a list or an array. First, I'm going to provide an array, and it'll just be an array of generic data, and then we're going to provide an index into the array. We want to determine where the index is in the array. So if the index is greater than or equal to the array length, that means we've gone past the end of the array here, and we need to loop back to the beginning. And to do that, we are just going to return the array at the index, but we're going to use the remainder operator with the array length. And all that's going to do is going to divide the index that we're currently at and divide it by the array length and then get the remainder. And when you get that remainder, it basically keeps you in the correct location in the loop by circling back to the beginning. The next case we have is if the index is less than 0. We want to pretty much do the same thing. We want to use the remainder operator. But since we are using a negative value for the index, it's going to give us a negative value back here. So in order to get back to the end of the array, we need to add back in the array length. And then the final case we will have is that the index is already within the bounds of the array, so we just simply return the array item at that index. That is the helper function, and I just want to copy that, and I'm going to create it again. But this time I'm actually going to use a list instead of an array, so then we can get list values as well. And it looks like I need to include, or I need to bring in the namespace for the generic collections. So now I can use lists, and I'm going to actually call this list instead of array. Let's rename that. And then instead of length, we're going to use the list count. Just rename these really quick. So we have those functions that will help us with our Polygon class. I have a static class here called Polygon Helper, and we're going to start implementing our triangulation function. So I'm going to call this, I'm going to make it a Boolean return. I'm going to call this triangulate. We are going to pass in an array of vertices that will define the polygon, and then we're going to pass out an array of integers that will define the indices of the triangles. I'm just going to call that triangles. And then I also want to pass out a string that will have an error message. So this function is going to return true or false, and that'll indicate whether it was actually able to triangulate the vertices that we provided. And then if it does return false, I want to return an error message describing why it failed. So first of all, let's go ahead and set our default value for the error message. That'll just be an empty string. Next, I want to do some basic checks. If the vertices passed in are null, then let's just go ahead and return false. And the error message will simply say that the vertex list is null. I also need to define this triangle list. So the default for the triangles is going to be null as well. Let's make sure the vertex list has a correct length to it. So if the length is less than 3, then we need to return false as well. In order to have a valid polygon, we need to have at least 3 vertices, and so let's make the error message. And then we could probably put an upper bound on this as well. You could say maybe the max vertices we're going to allow is like 256 or 512 or something like that. Just whatever number you think is appropriate. 1024. Again, I'm just picking a random number. I don't really have any reason for that. And we can go back and adjust this. It just seems like a relatively large number for a polygon. If it is more than that, I'm going to say that the max vertex list length is 1024, and then we'll return false. Okay, so these are just the basic checks to make sure that the data is basically in the correct format. Now we're going to go into some more complicated checks. If you remember from the last video, we specified some rules for the vertices. The vertices must define a simple polygon. And one of the main things we're going to check is if any of the vertices cross each other. So let's go ahead and make a function here that's going to check to see. I'm going to call this is simple polygon. And then we're going to pass in the vector of vertices that we want to check. And then we're just going to loop through all of these vertices in order and see if any of them actually cross. And I'm not actually going to implement this function right now. So I'm going to throw a not implemented exception. Today I'd like to actually focus on the polygon triangulation. In the next video, we can go through how to implement this function and check to make sure this is a simple polygon. But basically, you're looping through all the edges and making sure that none of the edges cross. So we'll just go ahead and throw that in here. If this is not a simple polygon, so I'm going to throw a not in front of it here, and we'll check the vertices. We are going to return false, and then let's tell it that the error message. Okay. And again, we're going to have to implement that later. In fact, I'm just going to comment this out right now since we are going to implement that at another time. In fact, we have a few more functions that I'm going to throw in here, just like this one. We're going to name them and talk about what they do, but we're not actually going to implement them until the next few videos. So the next one that we're going to have, that we're going to need to compute eventually, is going to determine if the polygon contains any collinear edges. And again, we're going to pass in the vector list of vertices. And for now, I'm just going to throw a not implemented exception. And that's something we would put right here. So if this contains collinear, if the vertices contain collinear edges, the error message would say something like, and we'll return false. Okay, but again, we're not going to implement that one quite yet. Next, we want to determine winding order. We want to, and you can make sure it's whatever winding order you want, but I'm going to use a clockwise winding order for all of my vertices. And if the vertices are passed in a counterclockwise winding order, then I'm actually going to make a function. We're just going to actually reverse the vertices so they're in clockwise winding order. So we're going to have a function that will be compute polygon area. And we'll pass it in the vertices. And this is actually going to have a void return. Here we're going to return the area. And then I also want to return something called the winding order. Winding order, there we go. So the winding order is not actually defined. That's just going to be an enumeration. So let's make an enumeration for the winding order. And this is another one of those functions that we're not actually going to implement right now. So compute polygon area, that's the next one we're going to do here. So let's go ahead and bring that in. So compute polygon area, we need to pass in the vertices. And we'll just pass out the area and the winding order. If the winding order, if it's invalid, then we need to return false. And we're just going to say an error message. If the winding order is, let's say or if it's counterclockwise, which is the one we don't want, then we're just going to reverse the array, and then they'll come out in clockwise winding order. Okay, and again, this is something we're not going to implement quite yet, so let's take that out. And once we get to this point, if we've implemented all these functions, we've determined that the vertices are provided to us in a correct format that we can use and triangulate the polygon. Since we're not actually implementing this information, we're just going to assume that the vertices are provided to us with all the correct information. So let's go ahead and get into actual polygon triangulation now. So if we go back here to our image, we need to make a list of all the indices in the polygon so that we can start grabbing the ones that we're currently working on and checking for new polygons. So all we're going to do here is make a new list of integers, and I'm going to call this the index list. And let's just loop through all of the vertices. And all we're going to do is populate the index list with the current index. Okay, so we're going to have one index for every vertex in the list. From the previous video, we talked about how we just keep looping around this and looking for ears until this index list has 3 vertices in it, or 3 indices in it. And once it has 3 indices, we're done. All right, so let's go ahead and go back to our code, and we're going to say that we want to loop while the index list count is greater than 3. I need to actually create the list of this triangle index data. I'm going to do that right up here. Actually, let's do that right here. So I want to calculate the number of the number of triangles. So the number of the triangle count If you look at our last video, the triangle count is just going to be the number of vertices minus 2, and then the number of indices. I'm going to call this the triangle index count, is going to be the triangle count times 3. Okay, so now that we know the triangle index count, we are actually going to create this array here. So the triangles array is just going to be a new integer array, and it's going to be the triangle index count. All right. And then I also want to make one more place to store the triangle. I'm going to change these because this is actually the total triangle count. So let's do that. And this one's going to be the total triangle index count. And then down here I have the triangle index count. And that is, in fact, maybe we'll just call that the index count. Okay, now I'm going to leave it the triangle index count. That's just going to be the current index where we are in this list of triangles. So every time we add a new index into this triangle list, we're going to increment this value so we can keep track of where we are. So with this loop, we'll come back to it in a little bit. But if the index count is greater than 3, then we're going to keep checking for new ears. But if it's not, that means we have 3 indices left in our index list, and that defines our final polygon, and we can just add that to our triangles list. So we're going to tell it that the triangles, we want to add some new indices at the triangle count. So that'll be the triangle index count. And we want that to be equal to the index list 0. And we're just going to add these in order. So at this triangle count, we're going to add 0, and then we're going to increment the triangle count. And let's do that 3 times to add the final vertices. And so we're going to add index list 0, 1, and 2. And that will add the final triangle to our list. So now let's go back up to this main loop here. So while the index list count is greater than 3, we want to start looping through all the indices in our polygon. So we're going to start at 0, and we're going to loop through all these until we find a valid ear. All right, so inside of our loop, let's create a for loop that will loop through all of the indices in the polygon. So that'll be the index list count, and then we're going to keep going until we get to the end. Okay, so we're now looping through all of the vertices. Let's go back to our image here of the polygon. As we start here, we want to get this index, and then we want to get the previous index, and we want to get the next index. So this will be index, whatever index we're on, -1, and this will be index whatever we're on, +1. And as you can see, doing a -1 is going to take us outside the bounds of the array, because that would give us a -1. But then we want to use our function to circle back to the end, and so we'll get 8 instead of -1. So in here, let's... I'm going to call this one vertex A. That's the one we're testing. The previous vertex will be B, and then the next vertex will be C. So let's get vertex A. So A is just going to be the index list, whatever index we're currently on. B is going to be the previous one, and I'm going to use the getItem function so that we don't go outside the bounds of the array, and we loop back to the beginning if it happens to be negative. So we're going to pass in the index list, and we're going to do I-1. Okay, and let's just copy that. And then index C, which is the next index, is going to do the same thing, but it's going to be a +1 over there. And so now we need to test these indices and find out if we have an ear that will be a valid triangle. And so if let's go back to our image here. The way we test that is, first of all, we need to determine is this angle convex? So we have the convex and we also have the reflex. Reflex are not valid ears, so we would just skip that one. But convex are good, so we want to see if that's what we are doing right now. And so we're just going to get the vertices at this point. So we're going to have a vector, let's call this vector A, and that's going to be from the vertices. We're just going to pass in index A, and we're going to do this for A, B, and C as well. So we're going to have vector A, vector B, and vector C, and we'll just pass in B and C. And we can determine if this is a reflex or a convex vertex by using the cross product. So I have the cross product viewer here, and here is what we are actually looking at. And this is approximately what the let's see, something like that if I look at the image. So it looks like that. Here's A, and then we have B to the left and C to the right. And so here is B, and then we have C to the right. That's approximately what the triangle looks like. And you can see we're getting a positive value. So if this value is positive, that means we have a convex angle. And if you watch this as I go, and it stays positive, positive, positive until the moment I hit there, and then it becomes 0. As the angle starts becoming reflex or greater than 180 degrees, we start getting a negative value. So as long as the cross product of A to B and A to C is positive, then we know this interior angle is going to be a convex vertex and is valid. So back in here, let's use the cross product. First of all, I need to define a vector that will point from, we'll just say vector A to vector B, and that will just be vector B minus vector A. And then the next one's going to be vector A to vector C, and that'll be vector C minus vector A. And by doing this subtraction, all I'm doing is creating vectors that look like this. I'm creating vectors that point from A to B, just like this shows, and then from A to C, and then I can take that cross product and get the information I need. If the cross product vector A to vector B and with vector A to vector C is greater than 0, or actually is less than 0, that means we have a reflex vertex, or the interior angle is greater than 180 degrees, and we can just continue. We don't need to keep testing. Okay, so, but if it's greater than 0, that means we have a convex vertex, and we can continue testing to see if this is a valid ear. All right, so the next test is we need to determine if any of these points are inside this triangle defined by A, B, and C. And so all we have to do is loop through all of these points and determine if those are in the triangle defined by A, B, and C. Let's go ahead and loop through all of the points in the polygon, and that'll just be the vertices. If any of these vertices are A, B, or C, we can just skip them, right? Because we don't need to check the vertices that are already on the triangle that we're testing. So let's do that test right here. So if J is equal to A, or if J is equal to B, or if J is equal to C, then we're just going to continue because these vertices, they're already part of the triangle that we're trying to test. And so now the test is we need to determine if the point that is J is inside the polygon that is defined by these three vertices. And so let's go ahead and do a triangle test. So we need a point in triangle test. Now we actually don't have this function yet. So let's go ahead and create that function. This is actually a point in triangle test. I'm going to call this is point in triangle. We're going to pass in the point we want to test, and then we're going to have the three vertices of the triangle, which will just be A, B, and C. And the way this works, let me go ahead and draw a picture here. So here is our triangle A. We'll just call this A, B, and C. And then here is the point we want to test. And I'm just going to call this point P. Okay, and we're just going to draw vectors in order. So one vector pointing from A to B, one pointing from B to C, and then one from C to A. All right. And then from A, we're also going to point to P, and then B is going to point to P, and C is going to point to P. We do three tests. We're going to compare the vector pointing from A to B with the vector pointing from A to P. All right, and we do the cross product. And what that looks like is, let's go ahead and bring up the viewer here. So here's the vector pointing from A to B. Okay, so that'll be this one right here, A to B. All right, and then we're actually going to say that A to P is defined as this vector A to C. And so what we're looking for is we want A to C, the cross product of AB and A to C, to give us this value over here. We want the point to always be on the right side of whatever A to B is. And if it is on the right side, we can see it's going to give us a negative result. Now, if it's on the left side, it's going to give us a positive result and tell us that we are outside of the triangle. And so all we have to do is come in here and now determine if the cross product is on the left or the right. Well, first of all, let's get some vectors that point from A to B, B to C, and C to A. So I'm going to have a vector pointing from A to B, and that'll just be B minus A, and let's just copy this 3 times. So we'll have A to B, we're going to have B to C, and then we're going to have C back to A. So that'll be, let's see, this one is B to C, so we're going to have B pointing to C, and then C pointing to A. And when you do the subtraction, this is what the vector always looks like. It's A pointing to B. So when you do B minus A, it's A pointing at B, this would be B pointing at C, and this would be C pointing at A. And now we need to do the same thing for the, we want A pointing at the test vector, and we want B pointing at the test vector and C pointing at the test vector. So I'm going to make an A to P, which would be P minus A. All right, and this will be B and C, and so here we'll have B and C. And then we have to do 3 cross products. So I'm going to call this cross 1 is going to be the cross product, oops, of A to B and A to P, and we can just copy this 3 times. Then we want to do, let's see, this one is B to C, and this one is C to A, and then over here this would be, this one would be B to P, and then this one would be C to P. And so as long as these are all negative, then we are good. If any of the cross products are positive, that means we're on the left side of one of them, and then we're outside the triangle. Okay, so if any one of the cross products is greater than 0, then we want to return false, indicating that the point is not in the triangle. Otherwise, if they're all less than 0, that means we are in the triangle, and we can return true. And actually, if they're less than or equal to 0, and if they're equal to 0, that means they're right on the edge of the triangle, and we're going to consider that an intersection with the triangle. So P will be considered inside the triangle if it's right on the edge as well. And so that's the point in triangle method. We want to determine if point P, and let's get point P. So vector P will be just the vertices at whatever our current J value is. So we're going to pass in point P, and then we need to pass in these vertices in clockwise winding order. And so if I look at the image, clockwise winding order is going to be, let's just start at B, so it's going to be B, A, and then C. So let's pass these in as vector B, vector A, and vector C. Let's see, does that work? Oh, did I not define that? Oh, is point in triangle. Okay, so I just named it wrong. So is point in triangle. So if the point is in triangle, then we know this is not an ear, and we can continue. So let's go ahead. So I'm going to make a Boolean value that is called isEar. I'm going to set it to false. Or I'm going to set this to true. We're going to assume that this is an ear when we get to this point. If we find one of the points in the triangle, then isEar is going to be equal to false, because one of the points in the polygon is in the triangle that we're testing, or the ear that we're testing. So we found one, we can break out of that loop. So this will break out of the for loop because we don't need to test anymore. Then we're going to come down here and let's test to see if this was an ear. So if this was a valid ear, then we need to start adding all of these vertices from this ear piece to the triangle list over here, and then actually remove this ear vertex from the list. So let's go ahead and write that in. So if it is an ear, we want to add these 3 indices, but we want to do it in clockwise winding order. So that is going to be B, A, and then C. So we're going to have B first, and then A, and then C, and then we're going to add them to the index count and increment it by 1 every time. So then we get to the next one there. And then from there, since we found an ear, once we've found an ear, we're going to remove this. So let's take that out of the list. So from the index list, we're going to remove at whatever point I is, and if we look up here, I is the current index we are on right now. From there we can just break out of this loop and go back to this main loop out here and keep looping back until we have an index count that is equal to 3. And I think that actually should do everything we want it to do. So let's just put some comments here. So this is first going to test is ear test vertex convex. Then down here, does this would be that does test ear contain any polygon vertices? Okay, so those are our two tests, and then we've actually succeeded. So we're going to add the triangles, triangle indices to our triangle list. We're going to remove the ear that we just found from the index list, and then we're going to break back, and we're going to come back over here and try to find another ear. Okay, so that should be everything. Let's go ahead and go back to our main game class, and let's see if we can implement this. So first of all, we need to have a place to store the vertices of our polygon. So I'm going to make a vector 2 here, and I'm going to call this vertices, and we'll just call this private. And then we need a place also to store the indices of our triangle. So I'm going to call this an integer array, and I'm going to call this triangles here. I've already created an array that has all of the vertex data for this polygon. And so I'm just going to paste that into our code. And in the initialization function here, here's the vertices of our polygon. And now I actually want to just draw the shape to the screen just to make sure it looks like what we're expecting. The flat engine library that we've created in previous videos does have a shape batching class that allows to draw polygons, and that's what we're using right here. So if you want to see how that works, obviously go to the other videos or download the source code and you can see what that looks like. But we're just using this to get something on the screen so we can see. Let's go ahead and run that and see what happens. Okay, so that looks good. That looks exactly like the polygon we have here, or really close anyway. So there's that, and then there's our polygon. All right. So now let's throw this vertex data into our triangulation function, and let's see what we get. So here inside of the initialization code, let's use the polygon helper, and actually don't have access to that. I think I need to bring in the namespace, so that'll be, let's see, the namespace will be the flat physics. There we go. I think that's where I put it. Yeah, that looks right. So let's bring in the polygon helper static class. So we're going to triangulate the polygon. Let's pass in the vertices. We're going to pass out the triangle indices. And let's pass out an error message if there happens to be one. And let's just test to make sure it works. So if this failed, we'll just throw a new exception. And we'll just say unable to. Okay, so let's just run this and see if it actually works. Okay, if we've gotten to this point, it means it sounds like it did something. At least it didn't give us any errors. Let's see if we can actually draw the results of our triangles here. So in my shape batcher, I'm going to make a new function, and I'm going to I don't think I have a function for this quite yet for drawing the triangles inside of a polygon. So let's make a function. I'm going to call this draw polygon triangles, something like that, or draw triangles. And let's pass in so we're going to pass in the vertices of the polygon. Let's pass in the triangle indices of the polygon, and then we'll pass in a color, and actually let's pass in a transform as well, just in case we want to do something with that. And so this really has nothing to do with the triangulation algorithm itself. I'm just going to make this real quick so we can so we can see what the results look like. So let's loop through all of the indices in the triangles array. Let's see, and I want to actually increment this by 3 since each triangle is going to have 3 vertices. And so let's get the indices of each one of these. So the first index is going to be triangles I. So we'll have A, B, and C, and we'll do I plus 1 and I plus 2. And then we can get the vertices. So vertex A is just going to be the index into the vertices array, so that'll be A, and then we can copy this and do it 3 times. So we'll have A, B, and C. So these are the actual vertex positions. So that'll be A, B, and C. Then I want to transform each one of these by whatever transform we've passed in. So that'll be VA by the transform. Let's copy that as well. So we'll do the same thing for each one of those, B and C. So we now have the 3 points in the triangle, so we can go ahead and draw them. So we're going to draw a line, and that is going to be VA to VB, and we'll pass in the color. Oh, and we need the thickness will just be 1. And we'll do that 3 times. So now we're going to go from VB to VC, and then we're going to go from VC to VA, and we have the color there. Okay, so I'm actually going to call this draw polygon triangles. Okay, so that should do it. Let's go back to our game class, and let's try to actually draw the triangles and see what happens. So we want to draw polygon triangles. The flat transform will just be, actually we don't need anything from the flat transform, so let's just create a generic one here. So this will just basically be an identity matrix. So the position, let's see, once a position will be 0, the angle will be 0, and the scale will just be 1. So we're really not going to transform it at all. We're just going to get what we have. Let's pass in the transform, and then the color, let's just do white, and let's see what happens. There we go. Okay. That looks like, in fact, that looks like exactly from our previous video when we started, when we went through this and we calculated all the ears, that looks like exactly what we calculated. So here was one of them. I think the next one ended up being down here, and then we went backwards from there and found one here, 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 and then here. So that is basic ear clipping for polygon triangulation. In the next video, I guess this is kind of an optional video if that's everything you want to know about polygon triangulation. But in the next video, I'm going to go and implement all of these functions to make sure we have a valid simple polygon. But for now, that's the algorithm for ear clipping and polygon triangulation.